Thank you. I slightly changed the title to be more general. I will be talking about the investigation of electron-mediated nuclear reactions. I have two co-authors in this study, and I'm very grateful to my colleagues who made the experiments possible. So first, a slide about the context and the background. Initially, with deuterium-loaded palladium, the idea was that we must look for ways to overcome the Coulomb repulsion for DD fusion. And then the situation becomes more uncomfortable with hydrogen-loaded nickel. It's much more difficult to explain how fusion comes about. Moreover, some experiments detected neutron, and Dr. Miley's Peterson cell type nickel electrolysis experiments has produced half of the periodic table as the output. So this point to the fact that there might be something more than simple fusion going on. In case of our experiment, our fuel consists of three elements: nickel, copper, and lithium. So notably, we don't have neither hydrogen or deuterium except for trace amounts. Theoretically, there could be some fusion process, or double electron capture is also exothermic, but it's quite a puzzle to explain how this process has come about. And this puzzle has inspired us to look into the role of electrons. Our experimental results have been published in volume 25 of JCMNS, and here I recap the main results. We only use thermal control in our reactor, so this makes high COP possible in theory. We have demonstrated continuous and controllable heat production, which is industrially very relevant. Our high operating temperature allows efficient heat to electricity conversion. We have a power rate of about 30 watts per gram of fuel, and from about 10 grams of fuel, we produced about 300 watts of heat. And our fuel is reasonably low cost and available. And we use bulk loading of fuel, so we put constant time foils and lithium into our containers. And so we don't need any nanostructuring or special preparation, which is good for scalability. And our reaction has been starting up without excessive waiting times. So I think these are quite promising results. And now we'll look into the analysis of reported data more. Here we see on the top temperature versus time. Time is in seconds, I believe. And there was constant power heating employed. And this chart highlights that we observed three types of processes in our experiment. First, you can see kind of electromagnetic noise. And you can see that this is non-exothermic because the slope of the heating curve doesn't change. And I would like to emphasize that such noise is absent from the calibration. So this is really coming from the fuel. And we're not sure what the source could be. Maybe it's some fracture in the material. Maybe it's something else. Then we have, with the red circles, indicate sudden temperature jumps. So these are chain reaction type sudden burst reactions. Then on the bottom, you see again time versus temperature, but on a much longer scale. And this process shows our continuous reaction process. Here, the red curve is a signal from a thermocouple that was close to the fuel container. And the blue curve is a thermocouple that was more far away in the reactor. And we have employed heating cycling. So we had heating up, then turned off the heating, cool down, heat up, cool down. And about 1,300 Celsius was the temperature at which we turned off the heating. And the red curve was giving the feedback for the temperature control, for heating control. So about half hour into the process, the continuous reaction has started up. And this time is about 3 hours. And you can see the temperature is overshooting quite constantly. And in the next slides, we'll zoom more into this. So for now, I would like you to believe that it's really a continuous power production process. And the big question is, are these three events precursors to each other, or are they somehow independent phenomena? I would like to point out the analogy with nickel-hydrogen systems. So earlier, Dr. Iwamura has presented the burst-like events with the nickel-hydrogen reactor. And Dr. Mizuno has reported in volume 25 of JCMNS very continuous exothermic power production, in that example from deuterium-loaded nickel. So very similar type of processes as we observed in our reactor. Again, the big question is, are we looking at the same processes or similar processes in different fuels? So now I would like to look more into the analysis of the burst-like processes. We produced a quite strong burst in our reactor. It has lasted a few seconds. And during that burst, we were monitoring the RF on a spectrum analyzer. It's hard to read the scale, but it goes from 0 to 10 megahertz. And this top part is the background. The peak in the middle is just a feature of the antenna. It had a higher gain in the middle. And these vertical lines are the radio broadcast channels. Now, when we had the burst, you can see that it's the same shape, but it has lifted the output power everywhere. So the reaction had a flat RF spectrum output. And during the same time, a Geiger counter, which was about ½ meter from the container, indicated about 40 times the background radiation. So I believe that this signal is consistent with the breaking radiation signature from electrons. Now, at that time, we could not measure yet the gamma spectrum. But I would like to refer here to a gamma spectrum measurement of a burst that was performed by the Martin Fleischmann Memorial Project. And they had very similar reaction conditions to our experiment, similar temperature. The red curve shows the burst signal. And again, if we look at the signal, this can be interpreted as electron breaking radiation from multiple energy levels. Also, I think it's important to point out next measurement, which is the blue curve, performed about 4 hours later, or the integration time was 4 hours later. And what we can see here is some kind of residue with energy level starting from maybe about 70 kiloelectron volts. And this, again, is very unexpected to see some kind of process at 7 kiloelectron volts still 4 hours after the burst event. And I would like to contrast Dr. Kasagi's presentation in the morning, which showed that during a continuous process, we don't have any such radiation signature. So there is some very distinct processes that are going on. Okay. Now let's look more into the continuous process. So here we again see the temperature versus time. Time is in seconds. And the top left chart shows the heating cycles. So at the left edge, you have the point where the heating is turned on. And where the lines end is the point where the heating is turned off. And we see here first 6 cycles before the continuous reaction started up. And then at some point, the heating reaction has, the continuous reaction has started up right away after heating was turned on. And in all the subsequent cycles, here this chart just shows 6 cycles. You can see a very distinct difference in the slope of the heating curves. And they are straight, which indicates that the exothermic power has been produced continuously. Now, at the same time, you can still see signatures of bursts. So if you look closely, for example, here there is a burst event, and here there is also a burst event which shows up as a temperature jump. So these kind of bursts occur both before and after the startup of the continuous reaction. Now the bottom right is the cooling cycle. So here the left edge is where the heating has been turned off, and the lines end when the heating was turned back on. So these curves correspond to the cooling before continuous reaction started, and this set of curves correspond to the cooling after the continuous reaction started. So what we see here is after the turn off the heating, the reaction still goes on for a few seconds, and then it stops. And the reason why the cooling is faster in these cycles than before is that this thermocouple is close to the fuel container, so it picks up the local heat, and the average reactor temperature is a bit lower than it was before, and this local heat dissipation is faster, and this makes these cooling curves appear to be falling down faster. So this is again an artifact which shows that we really had exothermic heat production coming from the fuel container itself. Now we looked at the long-term behavior of this continuous reaction by calculating the autocorrelation function of the temperature curve, and then looking at the frequency spectrum of this autocorrelation. Here on the top, we see the data for 20 minutes before the start of the continuous reaction, and this peak corresponds to the frequency of the temperature fluctuation. Now, in the bottom, we see the data for the 3 hours of the continuous reaction, and the peak becomes even more sharp as the transients fall away. And since our heating program is temperature feedback controlled, this very sharp autocorrelation peak proves that the reaction dynamics is very highly ordered, and this indicates there must be some reaction control parameter which regulates the reaction rate to a very constant value. We did not measure the radiation during this continuous reaction process, but I refer here to a report by Dr. Celani, where he reported observation of macroscopic voltage and current generation from Constantan wires. And this voltage and current indicates that there are some electrons which are shot out from the wires that can explain this phenomenon. So it somehow indicates that even during a continuous process, we are still dealing with electron acceleration and interaction. And I would like to refer to the measurements of Dr. Kasagi, which show that there is no measurable radiation signal above 100 kiloelectron volt. So whatever breaking radiation there is, it must be very low energy with respect to the nuclear energy levels. Okay. And we did an experiment with a different fuel combination. So in this case, the fuel consisted of nickel, aluminum, and lithium. And here on this chart, the green line shows the temperature in Celsius, and the horizontal axis shows the experiment time. This temperature was measured close to the fuel container. The yellow line shows the temperature at the edge of the reactor, and the blue line shows the applied heating power in watts. Now, in this experiment, the temperature was ramped up step by step. And at the start of this chart, the temperature program was a constant 1,350 Celsius. It was just previously ramped up from a lower value. Now, what you can see here is pretty uneventful for some time. Then where there is this first dashed line, you can see that temperature is slightly rising while applied power is falling. So that's a sign that something is starting up there. Second dashed line, you can see temperature rising more noticeably and applied power falling even faster. And around the red line, there was a runaway event that melted down the heating wires. So that's where the experiment stopped. Now, the main point I have about this experiment is firstly to show that there is not only one fuel combination with which the experiment is possible, but there seems to be multiple fuels that could work. So there is probably plenty of room for optimization by exploring different fuel mixtures. And the other one is about the temperature at which we notice these events. In case of the Constantine lithium experiments, we noticed the reaction events starting from 1,200 Celsius. This is slightly lower than the melting point of Constantine, but with some infusion of lithium, I think we can assume that the melting point is lowered to approximately this value. So I would say this corresponds to the melting point of the metal alloy. And here the reaction is starting from 1,350 Celsius, which corresponds to the lowest melting point in the nickel-rich nickel-aluminum alloys. So I believe that these temperature values have some significance there. Okay, so this was our experimental data. And any theory about what is going on must accommodate all of this experimental data. So I'd like to emphasize that it's not enough to explain just a small subset, but we really eventually need to explain everything that has been observed. All right. Since our experiments indicate that there are energetic electrons that are shot out, I'm interested in the interaction of the electrons and the nuclei. And I would like to first refer to the muon-catalyzed PD fusion experiments, where it was observed already in the 1950s that the muon is carrying away all of the 5.6 mega-electron-volt reaction energy. So this was explained by the muon being in very close proximity to the nucleus. Nothing similar has been observed for the electron until last year. And there has been a very important study, which I encourage you to look into, by Lipoglavchak group. They performed a PD fusion in graphite environment, and they observed some electrons which have been carrying away all of the 5.6 mega-electron-volt reaction energy. And I believe this is indirect evidence, but really points to the existence of a very close electron-nucleus proximity configuration, very much closer than inertial electrons. And perhaps it's a similar thing that is happening in our experiments. How could such configuration possibly come about? And I believe we have to look into relativistic quantum mechanics to look for an explanation. So what do we really know about the electron structure? Now, if we move with the electron, then this chart illustrates that by today, we have a quite clear picture that if we were to move along with the electron, we would see the electron circulating around the surface of a torus very fast. The first such calculations were made by Schrödinger, and he called this the Zitterbewegung motion. And in the 80-90 years since Schrödinger, we gradually improved our understanding. And I would like to highlight a publication in volume 25 of GSMNS by Celani's group, which has very nicely summarized our current understanding of this type of physics. And also the other papers are highlighted, I think, are quite important. Now, in this torus, the bigger radius is the Compton radius of the electron. And locally, the electron moves around at the speed of light. Now, since the electron always moves locally at the speed of light, the actual rotation frequency depends on the kinetic energy of the electron, because if the electron has a significant kinetic energy into one direction, then the observed frequency here changes to satisfy the speed of light local condition. So this frequency depends on the electron's energy, and this analysis is not unique to the electron, but exactly the same analysis can be applied to the protons as well. So the question arises, is there some combination of frequencies where we could possibly see a resonance which attracts the electron close to the proton? It sounds like a wild idea, but there has been one publication by Mr. Kalaon 2 years ago, which has explored this idea. And he has suggested that such a resonance could come about at 85 electron volt electron energy. Well, we don't know whether this 85 is true or not. I hope there will be some experiments that will verify it. But let's make the proposition that there is a certain electron energy level at which the electron experiences strong attraction to the nucleus. And most probably, this electron would be a chemically inactive electron. So the electrons in the shells, they already have considerable energy, especially the inner shell electrons. And the most interesting electrons are the ones where the gap to this special energy is small. So maybe these inactive electrons just need some small excitation by photons or phonons or plasmons that would raise their energy to this special transition energy. Okay, and perhaps nickel and palladium have such electrons which are close to this transition level. Okay, let's run with this assumption and see what it implies to the reaction dynamics. Now, this slide shows the process of melting in our fuel. I don't have time to go into the details of the phase diagram, but the point of the phase diagram is to prove that in our fuel there always exists a nickel-rich and a lithium-rich phase. They don't completely alloy together, but they like to separate into two phases. And there is a considerable Fermi energy level difference between the two phases, about 6-7 volts, I estimate. So what happens during the melting is that the ions, they get loose from the lattice, and they enter this zone where there is electric field according to the Fermi level difference, and they get smashed into the molten phase. So during the melting, we have these ions colliding into the molten phase, and that creates the setup where they may excite some of the electrons to this transition energy level that could then provide the close proximity electrons for enabling nuclear reactions. I like this model because this quite well matches our observation that we have exothermic energy during the melting phase, meaning the temperature rise phase, but zero or no energy during the cooling phase. Yeah, I should point out that Constantan doesn't have a fixed melting point, but it has a range of melting temperatures, and we adjusted the temperature cycling approximately to this range of the Constantan melting temperature. Now we can apply a very similar model to the diffusion across phase boundary in nickel-hydrogen fuels. It has been reported by Dr. Celani that fiberglass is important on the surface of Constantan. Also, Mizuno group reported that a layer of palladium is important in the surface. So I believe that this could create a Fermi energy difference on the surface. And instead of melting, in this case, we have hydrogen diffusion across the surface. And it was interesting to see earlier this week that Japanese colleagues came to the same conclusion, that this interface and hydrogen diffusion has a strong role in the reaction. And in the Dr. Mizuno's report, there is approximately exponential excess power to temperature dependence, which is what we would expect for controlling diffusion. And okay, so I will wrap up just in 2 minutes. We can make the same model again for the palladium deuterium fuels. So I was very interested to hear Dr. Schwartz's explanation about the presence of Antistokes line for the excess power. So this is the process which he has been explaining very well earlier this week. And we could interpret the Antistokes line as a phonon signature, and the electric field which is applied during electrolysis is pulling in deuterium ions into the lattice, and the impacting ions create then the phonon oscillations. So we have again diffusion across an interface which goes across some significant voltage. Yes. Yes. So I think I will wrap it up. And my conclusion is that to understand LENR, I think it's important to understand the dynamics of the electron. And we have, I believe, an industrially viable process. I did not give all the answers, what really happens in the reaction, but I think understanding electron is a first step.
Are there questions?
Okay, just for clarity, the first people that introduced the idea that electrons are important in the LENR field was Iwamura in 1995. But maybe few people know his paper because inside a big paper, so few people pay attention enough. So I think Iwamura, thanks a lot.
I have a question. Is your effect reproducible, and did you measure the temperature with more than one temperature measuring sensor?
It was shown in the slide that we have two thermocouples, so the red and the blue curve. And in terms of reproducibility, the burst-like events we can reproduce very regularly. The continuous reaction process we only had once. The last half year I was unfortunately wasting time playing with a better heater, because before doing next experiments I wanted to make sure that the heating element does not break up anymore, because the reason we stopped at 3 hours was not because reaction stopped, but because the heating element burned out.
Just one comment. There was a lot of data in the early 70s about proving the quark ideas about the nuclei, and then again in 93. One was Stanford inelastic high-energy electron scattering data, and the next one at, I think, was Jefferson Lab, was higher energy electron scattering, and it gave you the interaction of electrons with with protons and neutrons, basic protons primarily. That may be warranted to take a look at.
Yes, thank you. It will be very interesting to look into if you have the references.